Good afternoon and welcome to the Carl and Cymru for session number 2 for chemistry. This afternoon session will be run by Ms Stevens from Propane School. The session will last 45 minutes where she will go through the relevant subject content. If you have any questions, please use the question and answer section and we will endeavour to answer your question during the session. This session will be recorded with the recording and any resources uploaded to the e-sgol website, and that's in the Carl and Cymru area.
Thank you. Welcome back to the second session. Hopefully you found the first session useful. As that slide, which hopefully you can see now, outlines, tonight's session is about conservation of mass and trying to emphasise its link and its importance to, I'm sure, something you've all been baffled about at some point, which is balancing symbol equations. Okay, so it's something that has been relevant throughout year 10, but it's unfortunately something that hasn't gone away. It's something that you'll still have to get your head around throughout year 11. It tends to play a part, I would say, in every unit. So be it you're doing double award where they've got the 5 units or whether you are doing the 6 units in the triple, this is something that will be a central part and something therefore that's crucial for you to master if at all possible. Right, so as it says there, as our nice little police officer says, no atoms are made or lost during a chemical reaction, so the mass of the products equals the mass of the reactants. So the scientific law that this knowledgeable police officer is dictating is, as I'm hopefully sure all of you know, is the conservation of mass. Now, it's something that is therefore feeding directly into why you need to balance symbol equations and why that is so critical and kind of satisfies and then justifies that final mark in any balanced equation when you're given a balanced equation to do in an exam. So they're traditionally a balanced symbol equation with 3 marks, and they're quite distinct broken down marks where the examiner will give you 1 mark for being able to give the correct symbols for the reagents. So that would be the left hand side of the reagents. And then the examiner will give you a 2nd mark for being able to give the correct formula of all the products, so on the right hand side. And then the 3rd and crucial is for balancing it. So you've got to put the relevant number of moles, so putting numbers in front of either the reagents or the products in order to get it to balance each side. And that's because of the law of conservation of mass, because the law states that no atoms are made, or in that way, no new atoms are lost either during a chemical reaction. So the mass of the products has to equal the mass of the reagents. That is why it is so crucial when you are attempting to balance an equation. So if I go back to something that you picked up in the very early stages of year 10 knowledge, it would have fitted into that very first unit, or certainly the 2nd unit you did in year 10, where you were asked to calculate molecular mass. Now, this is something that will be touched upon next week again with Mr. Black, okay? But just in order to give you the required knowledge to be able to understand this session's content, just to go back and recap it for you. So the calculation of molecular mass is all related to, if not given the mass number, the top number in the periodic table. So if you recall, the periodic table supplied to you in an exam has both the top number, called the mass number, as well as a bottom number that relates to the number of protons, which is called the atomic number. Now, atomic number, as important as it is to calculate the number of protons and electrons, isn't relevant to today's content. So we're only going to concentrate on the top numbers, which is called the mass number. So if you want to work out the mass number of any compound, okay, or in that case, diatomic or triatomic elements potentially, then you have to mathematically work out the total of every single atom that's contained within that compound. So if you look at carbon dioxide, the mass number of carbon is 12, okay, and therefore there's only one of them. If there isn't a number, let's just recap in case anybody's confused. If there isn't a number behind it, then it's assumed to be 1. Now you could put that 1 in, and that'd be perfectly allowed of you. So you could have put the 1 in there just to signify that there was a single carbon, but often as chemists, we're quite lazy, and if it's no number, you assume there's only 1 of them. Now, as you can see there are 2 oxygens. Each oxygen is valid for a mass of 16. So 16, and there are 2 of them, signified by the fact that you've got this 2 here. So 2 times 16 is 32. And then if you total 2 of them to give you the total, then their MAR of carbon dioxide is therefore going to be equal to 44. Okay. The same sense, you got this is called sodium hydrogen carbonate, nitrate, sorry. So you've got Na, a mass number of 23. Hydrogen is a mass number of 1. Nitrogen has a mass number of 14. And oxygen, we've already seen, has a mass number of 16. So 23, only one of them because there isn't a number. But if you're more comfortable with it, you can put the 1 in there. Hydrogen, it's only one of them. Nitrogen, there is only one of them. And there are 3 of the oxygen. Now be careful, okay? It can get overwhelming and confusing at times when you see numbers, but don't forget the rule is the number here only relates to this atom here, the one that is directly before that number. So any number that's subscript as so, that number only relates to things directly before it. So do not get thrown. There is only one nitrogen. There's only a triple or 3 of that oxygen, okay? So one atom of N, which is 14. And then you've got those 3 atoms of oxygen totaling 48. So adding them all up together, it comes to a total of 86. Okay, so you need to get familiar and need to build up your confidence in working out this molecular masses, okay? So as I said, sometimes you can get a bit baffled by them. So this BAF is something I try to teach my pupils. So it's an acronym that's meant to trigger 3 key steps in order to do anything that's related to brackets. Now, brackets is another thing that tends to throw people. I did cover this with you last week in a session. So it's to do with the fact that if you've got brackets, you must remember to multiply everything within it. So some chemical formula will have those brackets, and if you then stick to the BAF rules outlined as follows is calculate the relative formula mass of whatever's inside the brackets. So that's the B in BAF. Then you multiply the result by the number A with after it. And then you add that total you've just calculated to the mass of anything that's in front of it. So BAF. Sounds confusing. It's better expressed as an example. So if I take you through this example here, what you can see is that you've got here the nitrate, which is the anion NO3 minus, okay? And because if you link it back to the crisscross rule of last week, magnesium is a cation by a charge of 2+, you need 2 of the nitrates to balance out the single magnesium 2+, okay? So that means the first step would be to calculate this inside first. Then second step, which is the A in BAF, is that you add it together, okay? And then anything in front of it would be then added to the magnesium here. So if I go through the steps, BAF, okay, first step is to work out what's inside the brackets, and inside the brackets total 62. The A is multiply it by the number after, okay, and you can clearly see that the number after is a 2, so you must multiply 62 by 2, giving you a total of 124. And then the F in the BAF is you add it to wherever is in front of it, and here the only thing that's in front of it is that magnesium, as you can see, and therefore magnesium has a mass number of 24. So you add 24 to 124, giving you a total of 148, okay? So if we quickly sweep through a few examples, some are naturally easier than others. As I say, when you start incorporating numbers or brackets, the complexity starts to build up. But if you notice the first one there, it's not too bad at all. You've got 2 singular atoms. Just an opportunity to remind you, take care here, okay? It is unbelievable how many times as an examiner you see people misread that. It's a single atom, it's a dual letter one, but it is a Cl, not a Ci. Be careful, okay? And I know it's really confusing because you do have carbon, which is C as a potential element, and you've got I, which is the symbol of Ig, that can also therefore be an element that can be included. But in this case, they would accompany it with a name of that element, okay? Now that element compound, the name of that compound would be sodium chloride. So that's just the trigger. If you listen to the word chloride, it tells you that therefore that must be chlorine, not a C and an I, okay? The examining board does try to make it clear between an I and a little l, a lowercase l, okay? But just in case you are using online resources or books, take care that you're not getting confused by those dual letter symbols, okay? So in this case, you've got sodium. Now, sodium is a mass number of 23. There's only one of them because there are no numbers anywhere near there. So just to be clear, let's just, so that you don't get confused by it. So 23, okay. Chlorine has a mass number of 35. Now, often on the periodic table, that's given us 35.5, okay? If that mass number isn't given to you, then assume it's 35.5. In this case, I've told you it's 35. So you can then add them up, okay? And then you've got the mass number therefore being equal to 58, okay? Same sense you'd have here. You've got nitrogen, which is 14. Get familiar with your calculators. Discussing this with the 11 pupils today, okay? You are expected to bring your calculator into the exam with you. Every calculator, you'd love to say, works in exactly the same way, but they don't. And the reality is you therefore need to get up close and personal with your own calculator so you're confident and familiar with how that calculator works, okay? Some will do multiplication before division, some have got a different setting in them. So the reality is, use your own, get familiar with it so you know exactly what happens, because we often as examiners see the correct method but the wrong answer, and often the reality is that the calculator's done it in an obscure way because they were using an unfamiliar calculator on that day. So in this case, you've got 3 hydrogens, so it's 1 times 3. Easy enough. That is 14 plus 3 therefore, which is equal to, is equal to 17. Oh, no one decided to vanish. Right. Now, the first two were relatively simple. Don't therefore get sidetracked with the second one. You can see there's a 2 and a 3 there. So you need to go quite quickly and rapidly. We'll go 27 times 2, because there are 2 of them. And you've got 16 times 3. Okay. So that one isn't too bad at all. I'm hoping that you can get your head around them quite rapidly. This is where I forget my own maths, but that does come to be a total of 102. Okay, this one is a requirement therefore you now apply the BAF. Okay, so calcium is 40, easy enough. Okay, then if you apply the BAF, then it's a case of inside the brackets is a 16 plus a 1, which is 17, but you have to apply that, multiply that by 2. So you get like double brackets essentially on your calculator, and that will give you a total of 74 and so on. Okay, so moving on to the slide, those are all the answers. I would suggest that you, if you aren't confident, then possibly you just go back and build a bit of confidence and practice them without the answers. And then if I go back quickly and just get rid of this and get rid of it, then maybe then when you go towards the recap, you can go back and revisit them, as Mr. Black was saying, on the Catalan website. Okay, then take the time, pause, try it, and then see whether you've got them right. Okay, right, so those are the answers. Now, this is where it gets the crux of what we need you to get your head around this evening, which is this concept of balancing. And it's fairly important. In fact, it's critical. So just before we finally prove the law of conservation, there is one more point to look at for, and that is balanced equations would always, or often at least, have numbers in front of the substances. So you can see them there. You've got the lithium, it's got a 4 in front of it, and then you've got the lithium oxide that's got a 2 in front of it. Now the relevance here is that that 4 will multiply everything there, and that 2, okay, will multiply all of this. So in a sense, what you've got in that is you've got 4 Li's and you've got 2 O's, because it multiplies everything, not just, so what I was saying earlier about the subscript multiplying only the thing directly before it, a full size number in front of a compound multiplies everything afterwards. Okay, so take care not to confuse by this rule of subscript only multiplying before. Compound wise, if there's a balancing before it, it multiplies everything. Okay, so in that sense, you'd have to multiply lithium oxide, which on its own as a molecule of Li2O would have a mass of 30. But then when you multiply it by 2, then obviously that side would equal 60. Okay, so this is the balance equation for the electrolysis of water. Now, some of you might well have got to this point already because it does sit into an unit. I think it's unit 3 in year 11 where you study metals primarily, but there's a subtopic within it called electrolysis. So this, if you haven't done it yet, don't panic, it will come around. This is how you can break down water into its constituent elements, which is hydrogen and oxygen. Okay, so you can see there that if I concentrate on the left-hand side, the water on its own has a mass of 18. Okay, but because there are 2 of them, that fundamentally equals then a mass of 36. Okay, and if you focus on the right-hand side, you've got 2 H2s, okay, which is therefore going to equal 4 because each hydrogen is a singular, and that means you've got 4 of them. And then oxygen has a mass of 16, and there are 2 of them in the diatomic molecule, and therefore equals 32. So if you add them up, it's 36 is equal to, on the other side, 4 plus 32, which, as always, and that is the aim of the game, you've got 36 both sides. And that's why balancing is so very critical. Okay, you have to be able to confidently balance these, because otherwise you are trying to break the laws of science, because no atoms can be made nor destroyed in any chemical reaction. That's the reality. Okay, so if the mass of the reactants doesn't equal the mass of the products, then unfortunately that is an indication that you've made an error somewhere in your working out. Okay, and therefore it's a point to go back if possible and check each of your calculations as being carried out correctly. Again, often the cause of any error is either typing too quickly into your calculator, or your calculator doing it in a bit of an abstract order, but that's why it's important you use your own equipment. Okay, right, so this one, more complex initially by the looks of it, but it's not something that I would say needs to panic you at all. Okay, this is again something that will be part of a later unit you'll do within year 11. It is going to fall into what is likely to be the final unit for double awarders, because it would fall into unit 5, which is where we do crude oil. Now this is a compound called propane. It's, most of you would have been familiar with it in things like camping gas, etc. But we'll come back to that, or you'll come back to that when you come across it in unit 5. For the purpose of this, I just want you to focus on the fact that that means you have 3 carbons and 8 hydrogens. Okay, you have, in a sense, 10 oxygen atoms there, because you've got 5 times 2, because it's diatomic. Okay, so you've got 10 of them. Okay, you can do it as a 16 times 2 initially, and then multiply the whole thing by 5, or you can multiply everything by 10, whichever you are most comfortable with. Some are quite strict in themselves, that they are more comfortable with having the bracketed calculated first and then they multiply, and that's all fine. There's nothing wrong with that. Okay, if you look at it then inside, if you look at carbon dioxide, CO2 has a mass of 44. Okay, so that's where the 44 comes from. Okay, that total is 44, and then multiply it by the 3, which comes before, and then water on its own has a mass of 18. So inside the brackets would be 1 times 2, which is 2 hydrogens, and a 16 for the oxygen. So total is 18, multiplied by, again, that 4. So if you look at the maths then, 44 plus 160, that would be, and you'll notice I've distinctly put them in different colours to be clear, this, and there's nothing wrong, and some of my pupils do it in exam and you can't be penalised for it. They literally put a line down their equation so that they are very clear. This is the left-hand side where I will put the reagents, and this is the right-hand side where my products will appear. Okay, not directly related tonight, but maybe a quick opportunity to remind you of the cruciality, how very, very important it is that you stick to this concept of reagents being one side, which is the left, and products being on the right side, okay? I'm fully aware that there is spatial limitations in an exam, but let's say if I took a balanced equation here, and I'll write the same thing here. So C3H6, apologies, okay, and you add 5 oxygens to it, okay. If you then get to the end of it, you put 3 CO2 and you've run out of space, you've got to the end of it, the worst thing you could possibly do then is go plus and then put the 4 waters here. I'm sorry that it's not clear, okay, but I'm hoping you're getting what I'm trying to get you to understand. The key thing should have been is that it has to lie to the correct side of the bond. So it's fine if you run out of space to go on to the next line. But if you're going to put on the next line, it has to go beneath the current product, and the 4 waters would then have to appear here. That is like the point of no return. So products have to distinctly lie on one side. So reagents on the left, products on the right. Okay, so hopefully you understand what I'm trying to get you to focus on there. But let's just get rid of that. And apologies if I've gone on a tangent, but it's actually surprising how common it is for simple marks to be lost by not adhering to that simple rule. So we'll put that one side on one side. So the yellows are all reagents and total 204. And then if you add up the products, it's 132 plus 72, which again, thankfully, totals 204. So conservation of mass is crucial and is something you must always adhere to. Okay, so balancing equations is extremely important and needs to be considered when writing any simple equation. So don't forget, as already emphasized, okay, atoms cannot be created nor destroyed, simply rearranged. So as basic as it might sound to you, I have before now bought in my child's Lego and got the concept across to them. So if you have a boat, let's say, made out of Lego bricks, yeah, you can dismantle all that boat and you can rebuild a plane out of it, okay? But that plane contains exactly the same building blocks, so Lego blocks, as the initial boat had, okay? So you can't suddenly, if let's say the boat contained 20 blocks, I can't make a plane that requires 24 blocks. Okay, in the same sense, if you start with a Lego boat that's got 10 blue and you only use 5 blues in the plane, then you have to make 2 planes to use up every single blue block that you had initially. So it's a bit like Lego. Yeah, you can shatter it into single pieces, which each atom would then constitute a Lego block, and you can rebuild it. But you can't get rid of any, and you can't suddenly materialize new ones out of nothing. Okay, so atoms can't be created nor destroyed. So if you're writing the balance equation for, let's say, hydrogen and oxygen, we know previously that water, I'm hoping all of you know that water is H2O. It's one of the most common compounds that most people can name quickly. First thing you do is you just give the formulas for each substance. Now that sounds easy, but I would use this opportunity therefore to highlight this to you. Okay, it is something that you're all aware of, but please, in the panic of an exam, do not forget this, which is that most gases are diatomic. Okay, now that is a word that I'm hoping all of you, I can't spell out. Let's try again and be able to spell this time. So diatomic simply means that it goes around. So di in chemistry means 2. They go around in pairs, okay? Most gases, just as all halogens, which is members of group 7, are diatomic in nature. So they'll go around with a partner in crime exactly identical to themselves. So it's H2, O2. There is no way around that. You can't, for convenience, decide, you know what? Because water is H2O, I don't want a diatomic molecule of oxygen. I'll just have a single atom. That's not possible, okay? Which is where this balancing will kick into place. So first thing, just put down the formula of each substance, but this is where you can't cheat. You have to put down the actual substance formula, okay? Second step, then check for any unbalanced element, okay? So because the formula, okay, of water is H2O, if you then focus on the fact that initially water in the formula only has a single oxygen there, O, but we know that oxygen is diatomic. That can't be, okay? If I start with 2 oxygen atoms, I have to use up both those oxygen atoms. And the only way to do that is, as highlighted there in red, is I will have to double and make 2 water molecules. I'll have to use both of them up, okay? So that's the first step. It doesn't really matter where you start. If you started with hydrogen in this sense, it wouldn't have really been an issue because you would have had 2 both sides, and therefore it's okay. But again, cut it halfway. If you start with the first one here, which in this case is hydrogen, if you keep checking from left to right, so check this, what you see is that there's 2 hydrogens there initially, and that's not a problem. But then continue your journey to check the next element within your formula, or the next formula, okay? And that's where the problem hits, because you can see clearly there that oxygen is diatomic and there was only 1 oxygen. So hence the reason for putting that 2 in front of the water. Step 3, though, is that you then check for anything that's suddenly become unbalanced or anything that wasn't balanced and you hadn't addressed yet. So in this example, as you saw earlier, if I go back to it, you have 2 hydrogens, but now you suddenly got 2 times 2, which equals 4, doesn't it? So I've now only got 2 on the left, but I've got 4, or I require 4 in order to make 2 water molecules. So the third and final step is to check the hydrogens, because we're only dealing with 2 atoms in this case. So you can see there, we need to double the number of hydrogen atoms, molecules in order to get 4 atoms. So suddenly, there's a 2 here, but there's also a 2 there. So if you check it, 2 times 2, okay, equals 4, that's fine. 2 times 2 equals 4, happy days. That equals 2, and then that times that equals 2 oxygens as well. So you've now checked every atom within the balanced equation. Neither requires any more adjustment, happy days. So that is how you attack a balanced equation. So if you go through a few examples now of word and symbol equations initially. First things first, something that you're all hopefully quite confident in by now, but just as a recap, in any word equation, the metal will always come first. Okay, so when you combine magnesium with chlorine, you must always remember to put the word of the metal initially in the name, so magnesium, okay? Then it is worth reminding you that unfortunately non-metals don't get to keep their identity, and often the ending will turn into 3 letters, which is I, D, E. So the non-metal has to lose its identity and change its ending, okay, and the metal comes first and keeps its name. So name-wise, you can see that the word one would be magnesium plus chlorine becomes magnesium and magnesium chloride. Okay, so that's where the IDE falls in. Okay, easy enough. So first step is that we have to apply what we went over last week, which is the crisscross rule, and use that to calculate what the formula would be for such a thing as magnesium chloride. Okay, so if I go back, let's choose blue because I don't have any blue in the diagram, so it'll be easier for you to see, or maybe better, let's go black. So magnesium, if you remember the rules we went over, we put the symbol in the box and we put the charge in the red box. Okay, we've got chloride. Okay, it's not got a number in the table of ions, so as I said earlier, we assume that's a 1. Okay, if you take that down then to there, and you take that down to there, the formula then would be Mg, and nothing comes down because there was 1 there, but you can put the 1 in there if you want. And then you've got the Cl, and this 2 has travelled down to be behind it. So that would be Mg, 1 if you want to put that in, or if not, then it's fine, Cl, and then that 2 came down. So applying the crisscross rule we did last week, the formula of magnesium chloride is MgCl2. Okay, so that's the first step. If you then put that in, if you then look, magnesium, cut that in half, How many have I got on the right-hand side? How many do I have on the left-hand side? So left-hand side, magnesium, I've got 1. Magnesium on this side, I've got 1. Great. So far, so good. So that's a tick, that's a tick. Chlorine, I've got 2. Okay. Then I've got 2 that side. So do you know what? That's a tick as well. So I've got 1 magnesium both sides, I've got 2 chlorines both sides as an atom, and therefore that balanced equation is exactly that, balance, and no further interaction or changes or adaptations are needed. Okay, so in that sense, have a bit of confidence and don't get scared that sometimes balanced equations don't require balancing. They're balanced exactly as they are. Okay, so that sometimes can throw over people. It's like, oh, I haven't put any numbers in front. That must mean I've gone wrong somewhere. Sometimes that 3rd mark is the easiest mark ever to gain because it's for having the confidence and sense to just not mess around with it. Don't touch it. Okay. They are quite rare, mind. And I will say that as an examiner, it's very rare for the balancing not to be required in some sense. There's usually a number somewhere if you look close enough. So the second example, got sodium and chlorine. Again, as I said, don't forget about the importance of changing that non-metal to an IDE. Okay, now sodium as a metal, you should be aware that metals are monoatomic. So as an element, it doesn't have a partner in crime. So if it's an element, it's a single one. So in this case, it would be Na. Okay, chlorine is a member of the group 7. So as a halogen, it is diatomic. It goes around with a partner. And then if you then apply, which I will show you again, the crisscross rule. In this sense, let's be careful. You've got Na, okay, it's got a 1, it's not 1, it's blank, okay, and then you've got chloride, also doesn't have a number, but we give it 1. Now, if I recap the rules we did last week, if the numbers are the same at the top, in this case, 1 and 1, you do not crisscross. Okay, you simply push them together, taking away the charges. So whereas it would be Na plus and Cl minus, the way of dealing with that would be to simply get rid of the charges, okay, and then push them together to give you NaCl. So with the numbers at the top, don't forget, don't crisscross, okay. So NaCl, confidently, hopefully now you're happy where that formula's come from. So sodium, as I said, is monoatomic. It goes around as a single. Chlorine, as a halogen, is diatomic, so it goes around with a partner. So you've got Cl2. NaCl then is the formula, and I've explained to you from the ionic rules that we did last week and the crisscross rules, we do not crisscross. The formula, therefore, of sodium chloride is NaCl. If you look at it then, this equation is not balanced, however, because if you do the counting game quickly, you've got 1 sodium. So if you do sodium, got 1 on that side, and we've got 1 on that side. So far, no problem. However, if you look at the chlorines, I've got 2 that side, and suddenly I've only got 1. Well, that cannot be allowed. As I said, you can't destroy any atoms. They can't vanish in this journey from reactant to product. Has to be accounted for somewhere. So in this case, you have to apply the balancing rules that we've been discussing so far this evening. So step 1, as I recap for you, write down the formula. Step 2, check for an unbalanced element. In this case, it was the chlorine that threw us. And then check for another unbalanced element. So journey from left to right, and this is important, okay? The journey from left to right should be repeated. So you go back and check back and forth until no more counting is required and the numbers on each side are equal. That is quite critical, okay? So be careful that you just don't do the journey once and then stop. You have to repeat it until everything is balanced. So in this case, as I outlined, you got 1 and 1 of the sodiums, but we had an issue with the chlorines that had too many on the left comparable to the right. So you can see there's 1 Na, but on the right hand side there, oh, see, typo. If I there's always one that I never pick up. So if you look, oh sorry, sodium is fine. So Na on both sides, but look at the left hand side, you've got 2 chlorines here, but only 1 there. So that's causing us then to have an issue. So an action is therefore required. When balancing, you may only place numbers in front of the element or compound's formula. Therefore, we have to put that 2 in front of the NaCl, not simply. It's amazing how many kids would just like to change the formula of sodium chloride to just being that, because that's easy. It requires less counting. Well, the reality is that's not how life works in chemistry. You have to stick to the rules of crisscross to work out the formula and then simply balance. So we can see that we've got 2 Cls now. So we fixed that problem of having 2 Cls. Happy days. But then, look, we've now got 1 Na, but we've now got 2 that side. Well, that can't be allowed either. So looking at the left-hand side, there's still 1 Na, but the right-hand side now has 2. Therefore, we need to do a further action, and that further action is to add this final 2 here. So now if you count the game, Na, I've now got 2 this side, and I've also got 2 that side, because you can see 2 Na, 2 Na. Cl, I've got 2, and I've now got 2 times 1. So 2 times 1, because there's 1 there. So 2 times 1 would mean I've still got 2 chlorines. So that is balanced, that is balanced. I've now got no further action required. So the balanced equation would be 2Na plus Cl2 makes 2NaCl. Okay, so you repeat, as I say, you have to repeat that more than once to make it certain that nothing else is required. But as you can see, by taking that journey one more time, just for safe checking, I'm now happy that I've got the same both sides. Okay, right. Third example, sodium and oxygen. Now this was one of the common reactions that you did in year 10, but again, the skills required for balancing is exactly as we've been discussing so far. So it's the group 1 element reacting with oxygen to make sodium oxide. As you can see, true to form, that ending is IDE, which is a non-metal losing its ending or changing its ending. Now, sodium is a metal, so it is monoatomic, it's a single. Oxygen is diatomic, so that might potentially cause a few problems when we get round to it. The first thing to do, as always, is let's work out what the formula of this says. So sodium oxide, sodium is Na. It hasn't got a number, so let's put 1 in. Oxygen has got a 2 minus charge. Okay, so apologies, my cursor didn't want to work. So 2 there. Taking that journey down, either side, crisscross, that means I've got Na, and beneath that subscript, I've now got the 2. And then I've got the oxygen, oxide, and no number came down, or if it did, it would be a 1, but that means we can ignore it. So as a formula, therefore, you can see that the formula of sodium oxide is Na2O. So that is exactly what we will use in our balanced equation, and we can't change it. It's stuck now. Na2O is the formula of what we've got. So we've got, okay, Na plus O2, Na because it's monoatomic, O2 because it's diatomic. Those are rules you can't change. That's the reality. And we've just proven that the formula is therefore going to be Na2O. Okay. So if we look at it, this equation is not balanced as it is, and therefore once more the steps to balance must now be followed. So you can see that we've got an issue with the sodiums and the oxygens this time. So if you look at it, if I start the journey from here, okay, so Na, and don't forget that is the halfway that we need to be careful of, then what we've got is we've got 1 Na and we've got 2. So that can't be. So the first step is I will change that into a 2 because I want 2. I want 2 both sides. Continue your journey onwards now, and let's focus on the next atom, which is oxygen. So this, you can see, is diatomic. So we've got 2 that side. So that means, great, I need 2 this side. But look, I've only got 1, which means I now need to put a 2 there. So far, so good. We've got a 2 in front of the Na. We've got 2 in front of the Na2O. But don't forget, I did tell you, you might have to repeat your journey from left to right more than once. So let's go back and start the journey all the way again. So start from the beginning again. I've now got 2 times 1, which is 2 NAs. But look, I've got 2 times 2. Okay, so 2 times 2 NAs now, which, as we know, is equal to 4. So what that means is that I now need to take that initial 2 and change it into the number we now want, which is 4. So if you think about the balancing and the rationale behind it, what we've established is that is therefore going to be the balanced equation. Okay, so you need 4 NAs, took more than one journey, but we got there. You need 1 molecule of oxygen, and that will be therefore able to form 2 Na2O molecule as a compound formula, Na2Os. Okay, balancing equation, as you can see, therefore, it's got a 4 Na and it's got a 2 there. So that was slightly more complex than the earlier example because you were unhappy or there was an issue with both atoms, in this case, the O's and the NAs. And the final one that I'm going to quickly go through with you is something that requires the crisscross rule to be applied potentially in more complexity, which is in tests. Oh, this is a point to point out to you. Table of ions, which we did recap last week. There is one element that appears twice in that table of ions. Okay, so and that ion is for iron. Iron will have 2 potentials. So you'll notice in the periodic table, in the table of ions, that you've got an Fe2+, which means it's lost 2 electrons. But beneath that, there is Fe3+. Now, name-wise, that appears after the iron. It says iron 3, and then beneath that one, you've got the Roman numeral 2. So be careful in the word equation that you're focusing on this bit, which is I'm asking you to make iron 3 oxide. So we're going to be using this ion from the table of ions. OK, so take care. Always good to double check that you're using the right ion. OK, right. So in this case, we've got iron in there and a 3+ because it did tell you that it was 3, and then you've got, if you go back to it, oxide. So oxide is the one we need. Oh, sorry, apologies. Oxide, put it in there. Okay, and it's got a 2- charge. There is no option or choice for oxygen. So putting those numbers in, you've got Fe and O. They don't change, and then they crisscross the numbers down, giving you that 2 to pair there and the 3 to pair there. So formula of iron 3 oxide is Fe2O3. If you then look at the requirements of this, what we've got is Fe, because it's a metal, it's a monatomic. You've got oxygen, which is O2, and Fe2O3, because I've just shown you using the crisscross rule that that has to be the formula and can't be changed. Even though we might want to change it, that is the formula. Okay, so again, not balanced because you can clearly see you've got 1 iron here, got 2 oxygens here, and look, I've got 2 and 3. So we're really not balanced there. So we need to address this and follow the rules. So the first thing we're going to do is deal with the fact that we've got 1 Fe there. Always good to cut it in half. If I continue that one down. Iron we're going to deal with first. Okay, we have 1 and we have 2. Okay, so putting in initial balancing, the first thing I'm going to do is I'm going to put a 2 there just so I can have 2 ions. Okay, then you continue on to the oxygen. Now I've clearly got 2 there and I've got 3 there. Now this is where you have to go back to primary school and think of your times table. Okay, what is the first multiple that contains 2 and 3? So in other words, in your times table, what was the first number that's divisible by 2, but also divisible by 3? And if you remember back to your 2 times table and your 3 times table, the first number that appears in both is 6. Therefore, I need to make 6 appear both sides. So we know that to get 6, we need to go 2 times 3. And to get 6 this side, it is 3 times 2. Okay, so that and that are now going to be crucial. Okay. So in order to get it to balance, I need 3 of those. So let's put a 3 there, and I need 2 of those, and let's therefore put a 2 there. Now, repeating the journey, and this I know we're getting short on time, but we'll squish it in, okay? We know therefore that if you repeat the journey and go back to what I had 1 ion initially, but I've now got 2, okay? But if you put 2 there, 2 times 2 here means I've actually required 4, okay? And therefore, the first thing to do is go back and change the 2 you put in earlier. And you are going to be putting in, therefore, 4 there, because you need 4 of them. So, balanced simple equation, therefore, is as follows. And it's a see, there's a typo, which I will change. There's always one. It's part of being an honest teacher to tell you, do you know what, I made a mistake, so let's change that, and I will change it properly. It's going to be 4, okay? But the corrected version will be put on the Catalan website, I promise. So there are true or false there. So we can create mass out of nothing. Truth is, no, you can't. You have to have conservation of mass. So what you start with is what you end up with. We can observe an increase in mass if one of the reactants was a gas. Well, that is true, okay, because what it will do is absorb it from the atmosphere, which we did initially weigh. So that's a true statement. If a gas is produced, it may escape into the atmosphere, so there would be a decrease in mass. Yes, if you are producing a gas and it bubbles away, you will mysteriously think that you are losing mass, but it's not being lost. It's just going into the atmosphere. So it would appear that the mass vanishes. And then we find the relative atomic mass by adding up the relative formula mass. False, okay. And then this is a balanced equation. Well, it is. So all of that, I'm hoping you found relatively useful. And you've now got a better understanding of how to balance equations. So thank you.
Okay, so I'll be taking next session, which will be session 3, and we'll be looking at identifying substances in chemistry, and particularly looking at precipitation reactions. So look forward to seeing you there. Thank you, Ms. Stevens, and good evening to you all.